Hello everyone, welcome to this Elevate 2025 presentation. In this session, we will be taking a look at how to use the .NET DataStore project, which was introduced in PowerBuilder 2025. This powerful feature automatically creates ASP.NET Core Web APIs directly from your data windows, which you can then use from any front-end client such as mobile, web applications, etc. Here's what we will cover in this video. A brief introduction to .NET DataStore, the advantages of using .NET DataStore, and the demo through which I will demonstrate the utilization of .NET DataStore. My name is Francisco Martinez, and I am a tech support engineer at Appian. I mainly work with C# development for applications and web APIs. My recent projects include the PowerBuilder Components app demo and the DW to Doc demo. So first, what is .NET DataStore? In a single sentence, .NET DataStore is a collection of tools and libraries to rapidly develop standard-compliant C# REST APIs based on the data window technology. So why leverage the .NET DataStore? It automatically generates REST APIs for your CRUD operations, cutting development effort and time. These APIs are front-end agnostic, ready to work with PowerBuilder or any other modern client such as Angular, React, or Vue. They provide seamless integration with PowerBuilder through the REST client object. All built on a standard ASP.NET Core architecture deployable on Windows, Linux, Docker, or on the cloud. And best of all, the code is easy to maintain and extend while preserving the familiar data window model your team already knows. Now let's talk about the project type, .NET DataStore. It was newly introduced in PowerBuilder 2025. This project type takes your existing data windows and converts them into C# model classes. Then, it automatically scaffolds a complete ASP.NET Core Web API, including models, services, and controllers that fully support CRUD operations. And it doesn't stop there. You can easily set up robust security with JWT, AWS Cognito, or Microsoft Entra. With just a few clicks, you will have a secure, production-ready web API. .NET DataStore allows this by supporting almost the same properties, events, and methods that you're accustomed to from non-visual data windows and data stores. Crucially, it supports all data window styles, data window expressions, dynamic data windows, and explicit transactions, including auto-commit settings. Plus, it fully conforms to modern C# standards, offering both synchronous and asynchronous programming paradigms. Here's a side-by-side comparison. On the top, you will see a familiar PowerBuilder data window script retrieving data using the setTrans object and retrieve. Below it, the equivalent operation using the .NET DataStore in C#. We create a DataStore object, assign the data window name, in this case the order customer, and call retrieve. As you can see, it is very familiar, and the context parameter here handles the transaction management, much like setTrans object in PowerBuilder. This design ensures that PowerBuilder developers can quickly adapt to the .NET environment without a steep learning curve. By default, the .NET DataStore project generates endpoints for interacting with the data window through REST calls, no matter the client. At the same time, it can generate endpoints specifically designed for working with PowerBuilder's REST client object, through which with a single call we can populate and update the data window with the web API. Those same endpoints can be used for child data windows. In fact, the REST client object allows to group multiple operations on the same transaction using batch data objects. Let's see this in action. First, let's imagine the following business scenario. Our customer has asked us to develop an ERP system for his company that can be accessed from desktop, browser, and on the go through a mobile application. We're mainly PowerBuilder developers ourselves, so our mind immediately goes to thinking of the domain entities, for example, employees, orders, products, and other entities pertaining to the business logic as data windows, and the business logic as working with data store operations. While we'll need external expertise to develop the web and mobile applications, it would be very inefficient if each team developed the access logic from scratch independently. Not to mention that having the database credentials on everyone's clients is probably not the best idea for security. Luckily, as PowerBuilder developers, there's something that we can do to easily centralize all domain models and business logic into a single entity that can then be accessed by all the clients, thus standardizing the data models, access, and increasing security by isolating the database server. Here's where the new .NET DataStore project comes into play. We can design the business models as data windows and then use the .NET DataStore project to generate a REST web API from them that can then be used from any type of client, mobile applications, web apps, and even from PowerBuilder itself. All the business logic can be centralized to a single location. In this project, we have already designed the business models as data windows, and we will proceed to generate a web API from them. To do this, open the new window, and in the Project Object tab, we will find the .NET DataStore. Let's add it to our project. In the project section, we can configure the name, location, target, and URL the web API will be listening in. We can leave everything else on default. In the converter page, we need to configure the database connection that will be used to connect and obtain the specific data types that each data window column needs to be able to appropriately generate the C# model. So, in the database profile selector, click Choose Connection and create a new database connection profile. In the Scaffolding tab, we can configure the parameters used to generate the controllers and services of the web API. The main setting to take a look at here is the template. This setting determines the endpoints that the controller will expose on the web API. Choose PB client when you only plan on using the web API with PowerBuilder's REST client object. Use non-PB client to generate a front-end agnostic REST API interface that can be used with any HTTP client. There is also the Any client. This will generate both sets of endpoints. By doing it this way, the generated web API can be conveniently used from both PowerBuilder and any other HTTP client. Because this is what we want, we'll select this option. Lastly, in the Security tab, we can configure the security paradigm that we want to use on our web API when communicating with it. We'll be taking a look at this later. With all the settings done, we can click on Generate Project to begin the process of web API creation. And that's it. We have just generated a web API from our projects to data windows with nothing more than a couple of clicks. The generated project exposes a basic CRUD API, which means it can create, read, update, and delete the entries in the .NET DataStore through REST calls, just like if it were a regular data store in PowerScript. And we can use these APIs to work with these objects from any front-end client. We'll explain the contents of this project after the next section. Now that we have successfully created a web API, we can implement this part of the business logic in our application. We will populate our data window control with data coming from the web API. Open the demo main window objects function list. In the load employees function, we will create a REST client instance, then use the newly introduced in PowerBuilder 2025 retrieve with model function, with the data window control and the URL of the web API as arguments. I'll wrap the statements inside a try-catch block to ensure that the REST client instance is destroyed correctly. Alternatively, the REST client could also reside at instance level. Next, for updating the data, I'll go to the update employee function. For this, the process is very similar. First, I'll create a REST client, and this time we will call the update with model function. This takes as parameter an additional boolean with which we can tell the function to call accept text on the data window before committing the update operation. If the data validation fails, the update will be cancelled. Finally, the load employee report function. Here, the approach has some additional steps because we want to perform all the retrieves and the one update inside the same operation to preserve data consistency. So, we will also need an instance of batch data objects to group all operations in a single batch. We'll load the data window child objects from the report, and then instead of performing the operation directly with the data windows and the REST client, we add the retrieve and update operations into this batch data objects instance. For the update, we can also indicate if we want the data window to accept text before performing it. Now, when making the call to the REST client's retrieve or update with models function, we pass the batch data object instance, and that's it. All the operations will be performed on a single transaction, meaning that if any of them fail, the entire thing will be rolled back and there won't be any changes done to the database. When implementing, pay close attention to transaction granularity and duration. Favor short-lived transactions, and where possible, use optimistic concurrency controls such as row version or ETAG to avoid locking up the production database for extended periods of time. We now start the Web API and run the application. We will see that our data window is displaying the data that we're retrieving through the REST client, just as if it were accessing the database directly. These Web APIs can be consumed not only from PowerBuilder, thanks to the fact that we selected any client on the .NET DataStore project. There is also APIs that can be consumed from any REST client, meaning that we can work with these data window-based models from mobile applications or any other frontend. Had we selected only PB client, it would have been a little bit more difficult to work with the data on the frontends. So keep this in mind when working on your projects. In this sample Vue web application that we will include in the project files, we can see that it also makes use of these same web APIs. Thanks to the .NET DataStore project, we no longer need to maintain the data access layer of two different projects, and we can now instead centralize it and focus only on the presentation. Let's explore the structure of the web API. By understanding how it's organized, we will be better equipped to maintain and extend it in the future. The project is organized into 3 layers, each with a clear responsibility. The data access layer manages all communication with the database through a central data context. The business logic layer exposes operations on domain entities in a storage-agnostic way. And the controller layer receives HTTP requests, invokes business logic, and returns formatted responses. This modular design lets you swap out or evolve any layer, for example, making changes to the database, adding mock implementations, or adjusting security without touching the rest. The data context class is our gateway to the database. It reads connection settings, opens transactions, and commits or rolls back changes. Under models, each C# class mirrors a data window. It holds the SQL query, display configuration, and column definition. These models encapsulate the mapping between database tables and in-memory objects. Services present a unified interface for each domain entity. Controllers rely on this interface, not the concrete implementation. This abstraction means that you can introduce in-memory or mock versions without altering the controller code. For example, the employee service interface defines all operations on employee records, and behind this interface, you can swap a live database implementation for a test stop seamlessly. Controllers are the API's front door. They validate incoming data, call the appropriate service methods, and format the results into HTTP responses. Each controller aligns with one or more service interfaces, keeping requests handling clean and focused. In the program.ts file, the application is wired together. Controller endpoints are configured, data context registration and connection setup takes place, and service interfaces are mapped to their default implementation. Notice how the data context is registered using the addScoped function. Scoped services are instantiated when a request arrives, and that instance is reused throughout the entire lifetime of that request, as opposed to transient services which are instantiated every time they're requested, and singleton services which are instantiated only once throughout the entire application. The central configuration file is where you change your database connection or switch service implementations for testing. Because the generated web API is standard ASP.NET Core Web application, we can easily work with it and modify it however we like. Following with our business scenario, our application has grown and there are a couple new requirements. We now need a view that displays the employee's order history in between specified dates, as well as some related statistics. There also needs to be an advanced search functionality with which we can dynamically change the columns to display, filter the orders by their dates, and also we need to be able to modify an order's tracking number for all of its items. Now that we have a web API with auto-generated CRUD endpoints delivering the core services, it makes sense to centralize all new business logic in the API layer so that both desktop, mobile, and web clients share the same rules. As requirements evolve, we can keep implementing features directly into the web API or exploit our PowerBuilder knowledge to implement as much as we can as data windows. For the first new requirement, we can implement it as a data window and convert it into the web API with the .NET DataStore project. But that is not a solution for the rest. For that, we will explore how to implement certain commonly used features in PowerBuilder in the web API. For extending the web API, we will be using the following features: SQL executor for executing SQL statements on the web API, the .NET DataStore's setItem, filter, retrieve, and update functions for performing the same operations as a PowerBuilder DataStore on the server, and lastly, DW Meta's create from SQL function for creating a DW Meta object from an SQL statement. We will use this object to create a .NET DataStore dynamically. The documentation for these objects can be found on the Appian documentation page. We go to the .NET DataStore section and click on the .NET DataStore API reference link. In here, we can find all the functions regarding the .NET DataStore, such as retrieve and filter, as well as the DW Meta's create from SQL function. The data context and thus the SQL executor is in the Snap Objects package, which can be found the same way. When working with embedded SQL statements, the generated web API can be extended with custom services that provide the data using those same statements. These services can then be consumed from any client. For business logic that involves multiple operations, we can make use of the .NET DataStore's backing entity, the data context. It allows full use of transactions to ensure data consistency on data operations with a syntax very similar to that of PowerBuilders. And for dynamic data windows, we can make use of the DW meta class createFromSQL function to create a .NET DataStore from an SQL statement at runtime. This is similar to using the PowerBuilder's transaction objects syntax from SQL function. For the order history, we already know what we have to do. We can model this view as a data window and use the .NET DataStore project to add it into the web API. Deploying the project preserves any API enhancements that we might have done to it. But for the other requirements, we will go into the web API and modify it ourselves. As a PowerBuilder developer, this might seem a little bit daunting, especially if you're not familiar with C# or ASP.NET Core. Fortunately, thanks to .NET DataStore being purposely designed this way, its C# syntax maps almost one-to-one to PowerBuilder's DataStore. This makes it incredibly simple for users to build custom extensions to the web API, and I'm going to show you how to do it. We'll begin with the function that provides the employee's oldest and most recent order dates to automatically narrow the search scope, and another one that provides statistics about the orders in between two dates. To create web API endpoints that provide this functionality, we'll use SQL statements and the SQL executor, so let's go to the C# solution and look at the changes that we need to make. Like it was mentioned in the beginning, services in ASP.NET Core applications work by being split in two. The interface, which defines the signatures of the methods that the service will provide, and the implementation that defines the concrete operations these methods perform. Code that wants to make use of a service requests it to the dependency injection container, which is where all the services are registered, which then provides the instance of the concrete service implementation that was registered. Here, registration takes place in the program.cs file. The client doesn't need to concern itself with the service's implementation, only the methods defined in its interface. This allows for a great level of flexibility where you can easily define a different service implementation, for example, one that uses in-memory storage or mock data, without having to modify anything in the existing client code. All this means that first we need to define the service interface with the methods that we'll need for this functionality, named iEmployeeReportService. The I stands for interface, and it's a code convention when working with ASP.NET Core Web APIs. First, we'll make the interface public so that it can be reached by the framework. Our first method will return a range of dates. So in order to improve data cleanliness, we're going to create a class that contains these two dates. Objects whose only purpose is to transfer data from and to the client are called data transfer objects, or DTOs for short. Let's create this class under an appropriately named folder. This dateRange DTO will be of type record, which is a special type of object whose equality is determined by the equality of its members. Back in the service interface, we'll declare the getEmployeeOrderDateRange method that will return a dateRange DTO, and we'll take an employee ID as parameter. Because we'll be working in the async paradigm, we'll wrap the return type inside a task object, and we'll append async to the method name for code clarity. Next, the getEmployeeStats function. For this, we'll also create a DTO that will encapsulate the employee's name, their total orders, and the total due for all the orders into a single object. This function will return this DTO and take an employee ID and date range from which to calculate the statistics as parameters. Now we define the implementation for this service in the input folder, named Employee Reports Service. This new class will inherit from the interface with the same name. I'll use the IDE's code autocompletion to insert the interface methods and a constructor. In here, we will request an instance of the data context to the dependency injection container. In the implementation for the getEmployeeOrderDateRange async, we will obtain an SQL executor instance from the data context. We will call the selectOneAsync method, passing the SQL statement and the employee ID as arguments. And because we're working with the async paradigm, we will add the keyword async to the method. With this instruction, we're telling the SQL executor to retrieve entities of type dynamic model, which is a special class which can dynamically hold objects of arbitrary members. To access these members, all we need is their names, which we know to be the columns in the SQL statement. Let's now import this object into the file. We return an instance of the DateRange DTO initialized with values of the dates. And we repeat the same procedure for retrieving the employee statistics. To finish our new implementation, we need to configure the dependency injection container with our service definition and implementation by going to the startup file and adding a new scoped service. We now create a new controller class using the API controller template. This will create an empty web API controller already decorated with the basic attributes. The root attribute specifies the URL subpath that will be matched to this controller. Using controller between square brackets is a placeholder that indicates to the framework that we want it to be matched to the name of the controller minus the controller part. This is by convention. There are other placeholders that we can use. For example, action will match the name of the method on the class. Let's use this one too. Now we'll define the constructor for our controller. We will be requesting the dependency injection container for our service and keep it as an instance variable. Now let's create our first endpoint for the employee order date range. Remember that we're working with async programming here, so we need to add the async keyword. And for the return type, we'll use a task wrapping an action result object. These objects configure aspects of the HTTP response, such as the status code and status message and response data, which in this case will be a date range DTO. Now to define the endpoint's code. Inside a try catch block, we'll invoke our service and return an action result object created from the OK function, which will set the status code to 200, which means success, and as a result, we'll forward our service return value. If any error occurs, we'll catch it and return a status code of 500, including the exceptions message. Remember the action part of the root attribute? This one also follows a convention. It will match the name of the method, but if it's declared as async, it will ignore the async part in the name. Now let's configure the endpoint. By decorating it with the HTTP GET attribute, we indicate that this endpoint will only be matched on requests of type GET. And by adding the produces response type attributes, we're helping documentation generators produce a more descriptive and useful output. We will follow a very similar process for the other endpoint. Here, if we don't obtain a valid result from the service, we return a different action result, one that configures the response to be a very familiar status code of 404. We will decorate it similarly as well. We already implemented the UI for these new requirements on the PowerBuilder application, so let's go and plug in the data retrieval code. In the getOrderDateRanges function, we'll create the necessary objects. We'll be making the request using the REST client and unpacking the DTO with a JSON parser. Inside a try-catch block, we will send a request with the REST client pointed to the URL of our web API and to the specific path of the getEmployeeOrderDateRange endpoint, passing the employee ID as a query parameter, and catching the response in the last argument. We do some error handling, finally extract the corresponding values onto the output arguments. Next, in the retrieveEmployeeStats function, we do the exact same thing. Create our objects, send the request, and parse the JSON response. With only this code, this window now obtains all its data through the web API, and the other frontends can consume it the same way. Let's test this by launching the web API and running the application. For changing the item's tracking number, we'll add an endpoint that lets clients update the tracking number for every item in a specific order. The client only needs to provide the order ID and the new tracking number. The workflow is validate that the order exists, update each item's carrier tracking number, and set its modified date. Commit the transaction or roll it back on error to maintain data consistency. I found it easier to model this functionality on a data window named the order detail CTN that retrieves and updates an order's item's tracking number. So all we need is to import it into the web API as a .NET DataStore using our existing .NET DataStore project. We will create a new service to provide the replace operation named order service. In here, we'll be doing the same operations as in PowerScript, just with a slightly different syntax. First, we'll begin the transaction explicitly by calling beginTransaction on the data context, which is similar to the PowerBuilder transaction. Then, inside a try-catch block, we create an instance of the .NET DataStore, importing any files that we might need. Here, we specify the data window object as a type argument when creating it. At the same time, the data context to use. We then call the retrieve function just like we would do in PowerBuilder, except that here we're calling the async alternative. We check if our retrieve operation has any results, and if it doesn't, we return a false value. We then iterate over each row with the .NET DataStore, update the columns with the setItem method, and invoke the updateAsync method. We roll back the transaction in the catch block in case of an error, and commit it if it's successful. Let's compare this with the PowerBuilder code, which would perform this exact same operation. As you can see, the logic and even the syntax is very similar and familiar. If we go to the .NET DataStore API documentation, we will see that there are a lot of other identical functions such as filter, sort, etc. Now with the service implemented, let's go to the program.cs file and configure it. Creating the controller is the same process as in the previous example. Back in PowerBuilder, first we'll consume this data using the same technique as the previous demo. Then, after the user selects an order ID and enters the new tracking number, we will use a REST client instance to call on the setTrackingNumber endpoint. Now on to the last requirement, the advanced search with dynamic columns. On a PowerBuilder app, one way we could approach this problem is through a dynamic data window whose definition is created at runtime from an SQL statement containing the columns we want to display. Fortunately, the .NET DataStore provides us with tools that do a very similar thing, creating a DW meta object from an SQL statement and then create a .NET DataStore from that DW meta. This is what we'll do. Return to snap develop and stop the project. We will add a new method to the iEmployee report service interface named getDataDynamicAsync that returns a NET DataStore interface and accepts an array of column names as strings, the employee's ID, an optional name pattern for the customer, and a range of dates. In the implementation, we will add a listing of valid column names that we accept. We will check that the columns passed to us are valid for security. And then we use the column names to create an SQL statement. If a customer name was provided, we add the corresponding statements to the query, and then use that to create a DW meta object and pass this onto the datastore.create function. This will create a .NET DataStore from the syntax. We then use the setFilter function to filter the data using the dates we received, apply the filter, and retrieve the data into the .NET DataStore. At last, return it. Because our search parameters are complex, it's better for them to be encapsulated on a data transfer object, thus improving code cleanliness and simplifying the request. We'll name this new DTO Advanced Search Request DTO and define it like this. The JSON property name attribute allows us to set a different JSON field than that of the class property. On the controller, we'll add the corresponding method expecting this DTO on the request body, indicating the distinction to the framework by decorating with the FromBody attribute. We'll unpack this object onto the service and return the result. Now, to use this new endpoint in PowerBuilder, we'll return to the IDE. In the Advanced Search window, Load Filter Data function, we will write a JSON string with the search parameters. PowerBuilder requires us to configure the data window before loading data onto it, but because we don't want to access the database from the client application to do this, I created a separate service that returns the data types for the columns, and then use that information to build the data window definition at runtime. The code for these components will be included in the project files for you to refer to. We'll make use of the REST client object to contact the web API, calling the endpoint through the REST client's send post request, passing the request string and dates as parameters, and getting a hold of the response. Lastly, we import that response into the data window with the import JSON function, and that's it. Let's run the application and we can see that everything is running correctly. And with this, we have finished implementing all the data access and business logic as Web API. Not only are we improving our native application security, but we are also making it more flexible by allowing the same business logic to be consumed from multiple frontends, centralizing all data access into a single location. As a side note, if we were creating an endpoint that returns a lot of data, transmission speed might be impacted, thus increasing perceived latency on the client and therefore affecting user experience. One way to solve this issue is to, instead of returning the entire dataset, return it in pages, giving control to the user on the amount of records per page. This will ensure that only a subset of the total results is transmitted, thus allowing the clients to display the data dynamically. The .NET DataStore takes this into consideration and has a specific method to retrieve data in pages, the retrieve-by-page method. It will allow us to retrieve a number of rows after a specified offset. By implementing a service and controller with this method at its core, we will be able to display the data in pages, reducing the network latency and improving the user experience. Lastly, before ending this video, I want to mention that while this approach is in fact much more secure than giving the applications direct access to the database, this will not prevent bad actors from getting access to the data. To help protect this side, ASP.NET Core Web APIs allow you to easily configure Web API authentication so that the endpoints cannot be accessed by just anyone. To work with this, the .NET DataStore project offers Web API security provider templates to get you started in securing the Web API. These templates include AWS Cognito, Microsoft Entra, and NoAuth 2.0 JWT authentication server, or you can also configure whatever you want. The details on how to implement this are outside the scope of this session, but I will leave links to the appropriate resources in the description. And that's it for this presentation. The projects used will be provided with the session. Thanks for watching. Now begins the Q&A section. I will be in the chat answering any questions you may have.
Now is Q&A time. Welcome to join our live Q&A Zoom meeting with the presenter. You'll find the Zoom meeting link at the top of the chat panel and also in the resources area below. Just click and join us live. You can enter the meeting from the Zoom app or your browser. Just type your name and click Join. You'll be in a waiting room until the meeting starts, and you'll join automatically once it begins. Now that you're in, you have 10 minutes to ask the presenter any questions about this session. Don't miss the chance.